I want you to do something for me right now. Just reach into your pocket or, maybe look down at your wrist.
Okay.
There is a very, very good chance that you are carrying a spy.
A spy. That is. That's a remarkably paranoid way to start things off.
Is it, though? I mean, think about it. It's completely invisible. It never, ever sleeps. It tracks your location probably to within a few meters. It knows when your heart rate spikes. It knows when you're sleeping. It probably even knows if you're slouching right now while you're listening to this. And it is constantly taking notes.
Okay, when you put it that way, I see your point, yes. We're talking about the sensors in our smartphones and our wearables. But, I mean, calling it a spy kind of implies it has malicious intent.
Okay, maybe not malicious, but definitely observant. Incredibly observant. But here's the thing. I don't really want to talk about them as gadgets today. I don't want to talk about which Apple Watch has the best battery life or anything like that. I want to talk about the ghost in the machine. Because all that data, we're talking millions of tiny numbers generated every single day. It creates something. It creates a data doppelganger, a digital twin of you constructed entirely out of data points.
And that is the absolute core theme of the source material we're covering today. We're doing a deep dive into machine learning for the quantified self, and we're drawing really heavily on the research by Mark Hugenborn and Burkhard Funk. And you're so right, it's not about the device, it's about the translation.
The translation, what do you mean?
Yeah, the translation of raw electrical signals into human meaning. Because your phone doesn't know you're running. It has no concept of what running is.
Right. It just sees numbers.
It just knows that a tiny spring inside a microchip is vibrating at a certain frequency.
Yeah.
The magic, and it really is a kind of dark art, is how we get from that tiny vibration to the realization, hey, you're training for a marathon. Or even, hey, you might be about to have a depressive episode.
And that right there is the roadmap for this deep dive. We aren't just reading the manual on how to use a Fitbit. We're going into the engine room. We are going to trace the entire life cycle of a single data point. From the moment it's born in a noisy, messy sensor, through the cleaning process, which is, wow, surprisingly messy, through all the math, and then finally to the insight.
It's such a fascinating journey because I think most people only ever see the end result. They see 10,000 steps on their screen. They don't see the millions of calculations, the filtering, the statistical gymnastics that are required to count those steps accurately without, say, confusing them for you just brushing your teeth.
Exactly. And to keep us honest, because let's face it, abstract math can get a little dry if we're not careful, we have two passengers with us on this journey. Two case studies from the text that really represent the two big sides of this coin.
Yes, the protagonists.
Yeah.
I think having them is just crucial to ground all the theory we're about to get into.
I love these guys.
Yeah.
So first up, we have Arnold.
Arnold, he's 25, and he is what the authors call the optimizer.
We all know an Arnold. Or, maybe we are Arnold. He's a total gadget freak. He's training for an Ironman triathlon. Right. He's got the watch, the chest strap, the cadence sensor on his bike, probably even a smart water bottle that tells him when to drink.
Oh, for sure.
He wants to know his VO2 max, his wattage output, his sleep efficiency down to the decimal point. For him, data is fuel. He wants to break records. He wants to optimize.
Precisely. He represents the whole performance aspect of the quantified self. He wants to push the machine, his own body, to its absolute limit. But then on the complete other end of the spectrum, we have Bruce.
Right. Bruce is 45. He isn't trying to win a race. He's just trying to stay stable.
Yes. Bruce is the manager, or maybe the healer. He's diabetic, and he's prone to severe depression. So he tracks his glucose, his mood, his activity levels, not because he's chasing a gold medal, but because he wants to avoid a hospital visit.
And the stakes for them are just completely different. If the algorithm fails Arnold, he might run a slightly slower 5K. He'll be annoyed. But if the algorithm fails Bruce, if it misses the warning signs of a depressive spiral or a dangerous glucose crash, the consequences are real. They're serious.
They are, and that is exactly why the mission of this deep dive is so important. We really need to understand how that raw chaos becomes the aha moment for both Arnold and for Bruce. We need to see how we take all that messy sensor noise and turn it into a sophisticated machine learning model that can actually help them live their lives.
So let's get our hands dirty. Let's start at the very, very beginning. Section 1, the raw materials. We have to talk about the hardware, the stuff that's actually in our pockets.
Sensors?
Yeah. The source material uses a dataset called crowd signals as a case study. And honestly, it is amazing how many senses a standard smartphone actually has. I mean, we all know about the camera and the microphone, but for the quantified self, we're usually looking at motion.
Right. And for motion, we talk about the big three. You have the accelerometer, the gyroscope, and the magnetometer.
Okay, let's break those down because I think a lot of people, myself included, honestly tend to mix them up. So, accelerometer. My first instinct is to think it measures speed, like a speedometer in a car. But that's not right, is it?
No, and that's probably the most common misconception. A speedometer that measures velocity. An accelerometer.
Yeah.
It measures force. Specifically, it's measuring acceleration forces that are acting on the X, Y, and Z axes of the device.
Okay, force. So if I have my phone sitting here flat on the table, it's not moving. Zero velocity. The accelerometer should read 0, right?
Wrong. It will read 9.8 meters per second squared, straight down.
Gravity.
Exactly. Gravity is a force. It's constantly pulling the phone down into the table, so the sensor is always feeling that pull. It's like its baseline reality. Then, when you pick up the phone and shake it, or when Arnold is sprinting, the sensor reads the intense spikes of force every single time his foot hits the pavement. It's measuring the impact and the change in velocity, not the speed itself.
Got it. Okay. Accelerometer is force and gravity. So what about the gyroscope?
The gyroscope is all about rotation. It measures angular speed. It tells the device how it's oriented in space. So, the simple version is it knows if your phone is upright or sideways. But more importantly, for our purposes, it knows how fast it's spinning or turning.
So if Arnold is on his bike and he leans into a really sharp corner, the accelerometer feels the bumps in the road, but the gyroscope is what feels the lean.
That's a perfect way to put it. It captures the rotational movement, and then to complete the trio, you have the magnetometer.
The compass.
Basically, yes. It measures the device's orientation relative to the Earth's magnetic north. In practice, it's often used to correct the drift from the other two sensors to help the system figure out exactly which direction you're actually facing.
And then on top of those three, you have things like light sensors, barometric pressure sensors, which can tell your altitude, so we know if Arnold is running uphill, and of course heart rate monitors on the wrist. But here's the problem the authors point out right away, and it's the first huge hurdle in our whole roadmap. These sensors are just firing continuously. They're just spewing out numbers constantly.
And this brings us to a really fundamental concept, granularity, or what the text calls the step size. In the math, you'll see this written as delta t. This is one of the very first and maybe one of the most critical decisions a data scientist has to make when they're building a system for Arnold or Bruce. How do we slice time?
Right, because you can't just feed a continuous, infinite stream of numbers into a computer. You have to chop it up into bite-sized pieces.
Exactly. So let's look at the trade-off here. Imagine scenario A. We set our step size, our delta t, to 60 seconds. So we take all the sensor readings that happen in a given minute, and we just average them all together.
Okay, that sounds manageable. You'd get one nice, clean data point per minute. Minute 1, average heart rate 80. Minute 2, average heart rate 85.
Simple.
It is manageable. The data plots look really smooth. It's very easy to handle computationally. You're not going to drain the user's battery or fill up their phone's memory. And for some things, it's great.
Like what?
Well, if we want to know if Bruce is generally sitting versus commuting, minute-level data is probably totally fine. You don't ship from sitting at your desk to driving your car in a split second. The transition is slow.
But I'm guessing there's a pretty big downside if we're trying to track Arnold.
A huge downside.
Yeah.
Let's say Arnold is doing interval sprints. He runs as hard as he possibly can for 10 seconds, and then he rests for 50 seconds.
Okay, a classic workout.
If your step size is 60 seconds, you average those two things together. The intense 10 seconds of all-out sprinting gets completely diluted by the 50 seconds of him standing still, gasping for air.
So the data just looks like a moderate walk.
At best, you've completely smoothed away the reality. You missed the entire point of the workout. You lost the signal and the noise. Or, by averaging, you created the noise.
Exactly. You lost the signal. So then we look at scenario B, a much finer granularity. Let's say our delta t is now 0.25 seconds, a quarter of a second. Now we're getting 4 data points every single second.
So the plots from that data are going to look totally different.
Completely. They look jagged, they're spiky, they have a really high variance, but And this is the crucial part. You can now clearly see the cadence of a step. You can see the distinct impact of a walking stride versus a running stride. For Arnold, this is absolutely essential information. But the cost is that you are now drowning in data, in noise, and the file size has become massive.
And what about the battery life on his watch?
It's tanked. Processing that much data in real time is incredibly expensive for a tiny little watch battery.
So the big takeaway here is that there's no single perfect setting. It's a trade-off. If you average too much, if you make delta too big, you lose the signal, the steps, the sprints.
Yeah.
But if you average too little, you just drown in noise and you kill the battery.
That's the core challenge. And that decision directly leads to the methodology they use in the book. They take these raw timestamps and they convert them into a structured matrix, which they call X. The rows of the matrix are the time steps, whatever size you decided on, and the columns are all the different attributes. But before we can actually do anything with that beautiful matrix, we have a massive, massive problem.
The problem of dirty data.
Precisely.
And this moves us squarely into section 2. Because sensors lie, or at least they get confused. The book describes this great scenario where Arnold's heart rate monitor suddenly reads 300 beats per minute.
Which, I mean, medically speaking, that's catastrophic. That's fibrillating heart attack territory for a human.
Right. So the question for the algorithm is Arnold Superman? Is he having a medical emergency? Or is this sensor just broken?
This is the entire challenge of outlier detection, and the authors are careful to distinguish between two types of outliers. Type 1 is a simple measurement error, sensor failure. The strap got loose, or maybe there was a static discharge, or a GPS signal bounced off a tall building. These are junk. We want to delete these.
And type 2.
Type 2 is genuine variability. This is the moment when Arnold actually pushes his limits. Maybe he hits 195 BPM during the final sprint of a race. Now, that's an outlier compared to his resting heart rate. But it's real. It's the most important data point of the day.
And that's the danger, isn't it? If you just blindly write a rule that says, delete everything over 180 BPM, you might accidentally delete the most interesting, most important moment of Arnold's training, his peak performance.
Exactly. You'd be sanitizing the data to the point of complete uselessness. So we need some mathematical ways to distinguish the trash from the treasure. And the text discusses a few main approaches. The first one is distribution-based. So think of the classic bell curve.
Right, the normal distribution. Most of the data clumps in the middle, and the really weird stuff is way out on the edges, in what they call the tails.
Right. And this is where they introduce a method called Chauvenet's criterion. It basically starts by assuming that your data follows a nice, symmetrical bell curve. Chauvenet's criterion then calculates the probability of any given data point occurring. If a point is so far out on the tail, let's say it's 3 or 4 standard deviations away from the average, that the probability of it being real is minuscule, then we flag it as an outlier and get rid of it.
So for something like a light sensor, this probably works great. If you're in a dark room and suddenly the sensor reads the brightness of the sun for 1 split second, Chauvenet's criterion says, nope, that's statistically impossible, and just cuts it.
But, and there's always a but, does human movement actually follow a neat bell curve?
I'm guessing no, because we do lots of different things.
Exactly. Think about Bruce's day. Most of the day, he's probably sedentary. He's sitting at a desk, maybe watching TV. That's one big lump of data, very low movement. But then maybe he goes for a walk after dinner. That's a second distinct lump of data medium movement. This isn't a single bell curve. The text calls it a bimodal distribution. It literally has 2 humps.
Oh, I see. So if you try to force a single bell curve onto that 2-hump data, the entire walking hump might look like a bunch of outliers because all those points are far away from the main sitting average.
Precisely. You would accidentally clean away all of his exercise because it doesn't fit the sitting curve. So to solve this, the experts suggest using what are called mixture models. Instead of trying to fit one bell curve, we mathematically combine multiple distributions to fit the data better. We'd use one curve for sitting and another curve for walking. Now, the walking data fits nicely inside its own normal zone and isn't flagged as an error.
That makes so much sense. It's like saying this is normal for walking, even if it's not normal for sitting. But the book also mentions a totally different way to find outliers. One that doesn't care about bell curves at all, the neighbor approach.
Yes, distance-based detection. This is a much more intuitive way to think about it. Imagine you plotted all of your data points on a piece of paper. If you have a big, dense cluster of dots in the middle, and then one lonely dot way off in the corner by itself, that lonely dot is probably an outlier.
Simple enough. If a point is far away from all its friends, it's suspicious.
But we can get a lot more sophisticated than that. The book details a method called the local outlier factor, or LOF. And this doesn't just look at distance, it looks at density.
Density, okay.
Imagine Arnold is out for a run. We have a nice, tight, dense cluster of data points representing his steady running cadence. Now imagine he stumbles for a second.
Okay, he trips.
We get a data point that's a little bit off. It isn't miles away from the cluster, he didn't teleport, but it's outside the tight rhythm of the run. A simple distance check might not even catch it because it's still pretty close to the running points. But LOF looks at the local density. It says, hey, the running points are packed together like sardines in a can. This stumbling point, though, is floating in relatively empty space compared to its immediate neighbors.
So LOF isn't just asking how far away are you, it's asking how lonely are you.
Yeah.
It compares the density around a specific point to the average density of its neighbors. It's designed to spot the odd one out, even if it's not a million miles away.
Correct. It's much more sensitive to the local context of the data.
So we've got all these different tools. Chauvenets for simple distributions, mixture models for complex ones, LOF for density. What's the final verdict for our case study? Do we use the fancy stuff or the simple stuff?
Well, it's interesting. In the crowd signals case study, the authors discuss that while the sophisticated methods like LOF are powerful, sometimes the simple safe bet is the best place to start. For things like light sensors, Chauvenet's criterion worked perfectly well to remove those impossible spikes. But for the accelerometers, they had to be much more careful.
Because you might throw out a real stumble or a sprint.
Exactly. The discussion in the text really leads to the decision that often the most practical first step is removing only the most extreme, statistically improbable outliers using a method like Chauvenet's. You just have to do that to avoid polluting the machine learning model later on. You don't want your algorithm learning that human running sometimes involves moving at 500 miles per hour just because of one bad GPS glitch.
Okay, so we've identified the trash. We've cut out the data points that claimed Arnold was running at the speed of sound. But now we've created a new problem. We have holes in our spreadsheet. Gaps.
Missing data. It happens constantly. Sensors fail, batteries die, watch straps loosen. We're left with these voids in our timeline. And this brings us to section 3, imputation.
Which is just a very fancy word for filling in the blanks.
It is. And there are some very basic, though not very good, ways to do this. You could just use the mean. If the heart rate is missing for 1 minute, you just fill it with the average heart rate of the entire workout.
But we already established that averages are kind of dangerous. If I'm doing intervals, the overall average is going to be completely wrong for both the sprint part and the rest part. It would just create a weird flat line in the middle of my spiky data.
It creates a flat line, exactly. It completely destroys the temporal structure of the data. A slightly better way, which the text discusses, is interpolation. Basically, you connect the dots.
Yeah.
If at minute 10, your heart rate was 140 and the sensor dies, and then at minute 12, it comes back on and reads 150, we can probably make a safe bet that at minute 11, it was somewhere around 145.
That feels much safer. At least it respects the trend in the data.
It works pretty well for things that change relatively slowly and predictably, like heart rate. But the book introduces the real heavy hitter of imputation and noise reduction, the Kalman filter.
I see this term everywhere. In engineering, robotics, navigation, the Kalman filter. It sounds almost mythical. How on earth does it apply to Arnold just going for a run in the park?
The Kalman filter is brilliant because it introduces the concept of humility to a computer program.
Humility, how so?
It operates on the fundamental assumption that it never knows the absolute truth. It only knows probabilities. And it operates on a constant cycle of 2 steps. Prediction and correction.
Okay, let's unpack that. Prediction and correction. Let's use Arnold as our example. He's running with his GPS watch.
Perfect. So, step 1, prediction. The Kalman filter has an internal model of Arnold. It knows physics. It knows that if Arnold was at point A 1 second ago and he was moving at, say, 3 meters per second, then the laws of physics dictate he should be at point B right now.
Right. Humans don't just teleport. We have momentum. So the filter makes an educated guess based on the last known state.
Exactly. That's the a priori estimate, the prediction. But then, step 2 happens. The sensor actually fires. The GPS pings a new location.
The measurement. And let's say the GPS is having a bad day. It's glitching. It says Arnold just moved 1 kilometer in 1 second.
Now we have a conflict. The internal prediction says he should be 3 meters ahead. The external measurement says he is 1 kilometer ahead. The Kalman filter now has to perform a reconciliation. And to do this, it assigns a trust value to both its prediction and the new measurement. This value is often called the Kalman gain.
Kalman gain. That sounds like a like a gym supplement.
It does, but you can think of it as a trust slider. If we know the GPS satellite signal is weak, maybe Arnold is running under some trees or between tall buildings, the algorithm assigns a high noise covariance to the sensor. It basically says the sensor is probably drunk right now.
So the Kalman gain, the trust slider, it slides more toward the prediction. It decides to ignore the crazy GPS reading and stick with the more plausible physics model.
Precisely. It smooths out that ridiculous outlier. It says, I don't believe you jumped a kilometer. I'm going to stick with the momentum I calculated.
But what if the opposite happens? What if Arnold actually did just start an all-out sprint?
Great question. If the sensor signal is strong, low noise, and it consistently shows him speeding up over several measurements, the trust slider moves the other way. It starts to trust the sensor more than its old model. It updates the internal model. Okay, my old physics prediction was wrong. Arnold has clearly accelerated.
So it feels like the algorithm is constantly having this little argument with itself. Physics says this should happen, but the sensor says that happened.
It is, and it's doing this hundreds of times a second. The final result is this beautiful, silky smooth line that represents the most probable truth, filtering out all the jagged, spiky noise from the cheap sensors we have in our pockets. Without the Kalman filter, your GPS track on a map would look like a zigzagging mess.
It's pretty incredible to think that just to track a simple morning jog, your watch is essentially doing the same kind of math that was used to help land the lunar modules.
It really is. And it allows for something called sensor fusion, too. You can combine the accelerometer, which is noisy but updates very fast, with the GPS, which is slow but generally more accurate, to get a perfect estimate of position. For the quantified self, the Kalman filter is really the gold standard for cleaning any kind of time series data.
Okay, so let's check our map. At this point in our pipeline, we have cleaned the data. We've removed the crazy outliers. We've used the amazing Kalman filter to fill in the gaps and smooth the path. We have a nice, clean matrix of numbers. But raw numbers still aren't insights, are they?
No, not at all. Knowing that Arnold's heart rate is 120 BPM right now doesn't tell us enough. Is he at 120 BPM because he's just starting to warm up for a run? Or is he at 120 BPM because he's been sitting on the couch watching a horror movie and he's terrified? Or is he at 120 because he's cooling down after a marathon? The number itself is meaningless without context.
Context is everything. And this brings us to Section 4, feature engineering. Specifically engineering features in what the text calls the time domain.
Right. We need to give the algorithm that context. And the main way we do that is by using the sliding window, which you'll see denoted by the Greek letter lambda.
The sliding window. I like to visualize this as a literal window frame that you just slide over your long strip of data.
That's a perfect visual for it. Imagine your data is a long film strip. Instead of looking at just a single frame, which is just one instant in time, we look at the last, say, 30 seconds of frames all at once. That 30-second chunk is our window. And now we can extract features from everything inside that window.
So instead of just having one feature, value of 120, we can now calculate summary statistics for that entire window.
Exactly. We can calculate the mean heart rate over the last 30 seconds, the max heart rate, the min. But more interestingly, we can calculate the standard deviation.
Okay, why is standard deviation so important here? I remember that from statistics class as a measure of spread, but how does that help Arnold's algorithm?
Think about the accelerometer data again. If Bruce is sitting perfectly still, the accelerometer reading is pretty much constant. It's just gravity. The standard deviation of his acceleration over a 30-second window is basically zero. It's a flat line.
Okay, makes sense.
But if he's running, that signal is going up and down, constantly with every step. The average acceleration might still be close to zero because the up and down forces cancel each other out over time, but the standard deviation will be huge because the values are spreading out really far from the center.
I see. So a high standard deviation in the movement sensors is basically a proxy for intensity.
That's it. It tells us how much action is happening inside that window. We can also calculate the slope across the window. Is the heart rate generally going up or down? A heart rate of 120 with a steep positive slope means he's probably starting a hard workout. A heart rate of 120 with a negative slope means he's recovering. That's crucial information that a single data point could never give you.
And the text mentioned something else that's really cool, these categorical temporal patterns. This is about the logic of before and co-occur.
Yes, this is for data that isn't numbers. Suppose we have activity labels that the user entered, or that a previous simple model guessed. We want the new model to find patterns like The user was labeled as inactive before the activity became running, or the user was labeled driving before walking.
It sounds almost like storytelling logic. First, this happened, and then that happened.
It is. The algorithm looks for these sequences. The book calls them B for before and C for co-occur. But we can't just list every single sequence that ever happened. That would create millions of useless patterns. So the authors introduced the idea of support thresholds, denoted by theta.
Which basically just means, does this pattern happen often enough to actually matter?
Yeah. Right. If the pattern inactive before running appears in 50% of Arnold's data logs, that's a very strong pattern. The algorithm keeps it as a useful feature. But if the pattern cooking before skydiving happens only once, the support is way too low, and we discard it as a coincidence. It's a mathematical way to filter out the random coincidences to find the underlying habits.
I love that. Using math to separate habits from coincidences. Okay, so we've looked at engineering features from time, but the book takes a hard left turn here, straight into physics class. We need to talk about the frequency domain.
Section 5. And this is where things get really, really interesting, especially for rhythmic activities like walking or running.
Right. The authors call it thinking in waves.
Exactly. You mentioned earlier that when you plot walking data over time, it looks jagged, up, down, up, down. But if you look at it from a different perspective, walking is a rhythm. It's a periodic motion. It's a wave.
And to see that wave, the text says we need to use the Fourier transform. Now, I have heard this is one of the most important mathematical concepts in all of engineering, but it's a bit dense. How can we explain this simply?
I think the best analogy is a musical chord. Imagine you play a C major chord on a piano. Your ear just hears one complex sound, a single clang. But we know that that sound is actually made of 3 specific notes, C, E, and G each, vibrating at a very specific frequency.
And the Fourier transform is like a magic machine that can listen to that single clang and break it back down, telling you this sound contains a C, an E, and a G.
Perfectly put. Now, just apply that exact same logic to Arnold running. His raw accelerometer data is the chord. It's a messy, complex mix of vibrations, his feet hitting the ground, his arms swinging, maybe even the vibration of a car passing by on the road. The Fourier transform takes that messy signal and breaks it down into all its individual component frequencies.
And what are we looking for in that breakdown?
We're looking for the fundamental frequency. Basically, the loudest, strongest note in the chord. If Arnold is running, his body is bouncing up and down in a very rhythmic way. Maybe he's taking 3 steps every second. The Fourier transform will show a massive spike in energy at 3 hertz.
Hertz just meaning cycles per second.
Right. So if we run the transform and see a strong spike at 1.5 hertz, we can be pretty confident he's walking. If we see a strong spike at 3 hertz, he's probably running. If we see no clear spikes at all, just a lot of random noise across all the frequencies, he's probably doing something non-rhythmic, like brushing his teeth or washing the dishes, movement without a clear pattern.
That is so cool. It's identifying the activity by its music.
It is. And this insight actually leads us to another more advanced type of data exegeting, a technique called low-pass filtering.
The text mentions the Butterworth filter.
Yes, that's a common type. Think of this as cleaning up the audio. We know from a biomechanics perspective that human beings physically cannot vibrate at 50 hertz. We aren't hummingbirds. We're not power tools.
I can confirm I definitely cannot vibrate 50 times a second.
Right. So if the sensor shows a strong vibration at 50 hertz, it is, by definition, machine noise. It's probably the engine of the car he's sitting in, or some kind of electrical hum from nearby equipment. So we apply a low-pass filter. It literally lets the low frequencies pass through, and it cuts off or attenuates the high frequencies.
So it sets a ceiling. It tells the algorithm anything vibrating faster than a human is physically capable of must be noise, so ignore it.
Exactly. By cutting out that high-frequency noise, we're left with a clean, smooth signal that represents only actual human movement. This makes it so much easier for the machine learning algorithm to figure out what Arnold is really doing.
So we've engineered all these amazing features. In the time domain, we have slope, mean, variance. In the frequency domain, we have the fundamental rhythm and the energy at different frequencies. But now we have a new problem. We've created too many features.
Ah, yes. The curse of dimensionality.
It sounds like a bad sci-fi movie title. But can you explain why having too much data is actually a bad thing? I thought big data was the whole goal.
Big data is the goal, but wide data can be a huge problem. Let's just look at our sensors again. We have the accelerometer with its X, Y, and Z axes, that's 3 columns. The gyroscope has X, Y, and Z, that's 6. The magnetometer has X, Y, Z, that's 9 columns already. Then we calculated the mean, max, min, and standard deviation for each of those 9.
So now we're at, what, 9 times 4 is 36, plus the original 9.
Yeah.
We're at 45 columns.
Plus the Fourier peaks we just talked about, plus heart rate, plus barometric pressure. It's not crazy to think we might have 100 or more columns of data, all describing a single second of Arnold's life.
And the poor machine learning algorithm has to try and make sense of all of that at once.
And it gets overwhelmed. It's too much information. It starts seeing patterns that aren't really there. It's called overfitting. It might start thinking that the magnetometer z-axis standard deviation is the key reason Arnold is running, when in reality it's just correlated by random noise.
So we need to simplify. We need to somehow distill the essence of the data without losing all the important information. And this brings us to Section 6, Dimensionality Reduction. And the star of this section is PCA, Principal Component Analysis.
PCA it's magical, but it's also very abstract, so we need a really good visual here to make sense of it.
The outline suggests the baguette analogy. I'm getting hungry, so let's go with that.
Okay, perfect. Imagine a cloud of data points floating in three-dimensional space. And let's say, just for this example, that this cloud is shaped exactly like a baguette, a long, thin loaf of French bread.
Okay, I'm picturing a data bread loaf floating in the room right now.
Good. Now, to describe the location of every single crumb inside that loaf, you could use its x, y, and z coordinates. It's 3 dimensions, 3 numbers for every crumb. But just looking at the shape, what's the most important thing about a baguette? It's its length. That long axis is what defines it.
Right, that's where most of the bread is. It's mostly length.
PCA is a mathematical technique that finds that axis. It draws a line straight through the longest part of the data cloud and calls that line Principal Component 1. It is the single dimension that captures the most variance, the most information about where all the crumbs are.
Okay, so it finds the most important direction.
Then it looks for the second most important direction, which has to be perpendicular to the first. For a baguette, that would be its width. That becomes Principal Component 2.
And the third direction, the height or thickness, doesn't matter as much because it's roughly the same as the width. There's not much new information there.
Exactly. So what PCA tells us is, hey, you don't actually need X, Y, and Z. You can describe 95% of the location of every crumb in this baguette just by knowing how far along the length you are. We've successfully reduced 3 dimensions down to 1, and we've barely lost any meaningful information.
So bring this back to Arnold's running data.
When Arnold runs, his arms are pumping, his legs are driving, his torso's twisting, all the sensors are screaming with data. But really, they're all screaming about the same underlying thing: forward intensity. PCA finds that underlying master variable. It condenses those 20 or 30 noisy sensor columns into, say, maybe 3 or 4 principal components. PC1 might represent forward motion, PC2 might represent lateral sway, PC3 might be vertical bounce.
And suddenly the machine learning algorithm only has to look at 3 or 4 clean columns instead of 30 noisy ones. It becomes faster, more efficient, and often more accurate.
Yes. The big trade-off, though, is that we lose the names. We lose the interpretability.
Right. PC1 is just a mathematical construct. You can't point to it and say, that's the accelerometer z-axis. It's a weird blend of everything.
It is. So you trade that easy interpretation for a huge gain in power and efficiency.
Okay, we have covered the numbers inside and out, but we haven't talked about the words. We have to remember Bruce.
The manager.
Right. Bruce isn't just generating heart rate data. He is also journaling. He's writing about his depression. I feel sad today. I am exhausted. That's completely unstructured data. It's not numbers.
And this brings us to Section 7, Unstructured Data in NLP Natural Language Processing. This is so crucial for the quantified self because so much of our internal state comes out in our words, not just our heartbeats.
But computers don't read English. They need numbers. So how on earth do we translate Bruce's diary into something a spreadsheet can understand?
It's a pipeline, very similar in spirit to what we did with the sensor data. Step 1 is tokenization. We just chop the sentences up into individual units or tokens. I feel sad becomes 3 tokens. I feel sad.
Simple enough.
Step 2 is stemming. We want the computer to understand that running, runs, and ran are all the same core concept. So we use an algorithm to chop off the endings. They all become the root stem run.
That makes sense. You don't want the computer to think run and running are 2 totally unrelated different activities.
Step 3 is stop word removal. We just delete all the fluff. Words like the, and, is, a, in. These words appear constantly but carry very little specific meaning. So a sentence like, the man is running fast, just becomes the tokens, man, run, fast.
Okay, so after all that, we're left with just a bag of important words, literally.
That is the actual technical term. It's called the bag of words model. In its simplest form, we just count the words. Bruce used the word sad 5 times this week. That count becomes a feature for our model.
But there's a nuance here, right? If Bruce writes the word "the" 50 times in an entry, it doesn't matter at all. But if he writes the word suicidal just once, that matters immensely.
This is where a more advanced technique called TF-IDF comes in. It stands for Term Frequency Inverse Document Frequency. It's a real mouthful, but the concept behind it is beautiful.
Okay, break it down for us.
So, term frequency, TF, is just what we said. How often did this word appear in this specific entry? High frequency means it might be important, but inverse document frequency, IDF, asks a different question. It asks, how rare is this word across all of Bruce's diary entries?
Ah, I get it. So if Bruce uses the word tired in every single diary entry for a year, its IDF score is going to be really low. It's not a unique or special word for him, it's just his background noise.
Exactly. But if the word exhausted appears only once in 6 months, its IDF score is going to be huge. The algorithm flags that word as highly specific and highly significant for that particular day. TF-IDF is a weighting scheme that helps the machine learning model ignore the common words Bruce uses all the time and focus on the rare descriptive words that might signal a real change in his mental state.
That is incredibly smart. It's like a mathematical way of highlighting the anomalies in language, just like we highlighted the anomalies in his heart rate data.
Precisely. It's all about finding the signal-to-noise ratio, whether that noise is electrical interference or just common language.
So, we've done it. We've reached the end of the pipeline. Let's just take a second and look back at the map of this whole journey.
We started with our 2 protagonists, Arnold and Bruce. We took their raw, chaotic, messy sensor data. We had to first decide on a granularity, a time slice. Then we had to clean the dirty data with things like Chauvenet's criterion and a local outlier factor. Then we had to fill in the gaps with interpolation and, most powerfully, the Kalman filter.
And then came the artistry. We engineered features. We looked at the time domain to find slopes and variance within a sliding window. We jumped to the frequency domain using Fourier transforms to find the hidden rhythm of his movements. We used PCA to simplify the overwhelming mess. And we even used NLP to decode the meaning in Bruce's diary.
And only now, after all of that work, do we finally have a data set. A clean, rich, structured matrix of numbers that is finally ready to be fed into an actual machine learning model.
It really highlights that thing you always hear data scientists say, that machine learning is like 80% data preparation.
It is. The actual learning part, the neural networks, the decision trees, all the cool stuff, they are completely useless without this rigorous, thoughtful preparation. This entire process we just described today. That is the difference between having a fancy pedometer and having a real digital health coach. It's how we move from just counting steps to actually understanding intent.
And that leads me to my final thought for you, for the listeners. We've spent this entire deep dive talking about how we can clean and interpret the data we generate, how we can build these digital twins of ourselves.
We are, bit by bit.
But consider this. As these algorithms get better, as the Kalman filters get smarter, as the feature engineering gets deeper and more creative, this digital twin is going to start predicting your states better than you can.
It will know you're getting sick a day before you feel the first symptom. It'll know you're sliding into a depressive state before you admit it to yourself.
Exactly. So here's the question I want to leave you with. If the algorithm says you are tired, but you feel fine, who's right? Do you trust your own feeling? Or do you trust the ghost in your pocket?
That really is the ultimate question of the quantified self, isn't it? Are we measuring ourselves to better understand ourselves? Or are we measuring ourselves to eventually replace our own intuition?
Something to mull over on your next run. Thanks for diving deep with us today.
A pleasure, as always.